Welcome to the New Chemists podcast. We are so glad you are listening. Feel free to subscribe on Spotify and tell your friends and colleagues about the podcast.
Welcome to the New Chemist podcast.
Bienvenidos al podcast del nuevo químico.
Καλώς ήρθατε στο podcast του New Chemist. Welkom bij de podcast van The New Chemist.
Bienvenue sur le podcast du nouveau chimiste.
Bem-vindo ao podcast do novo químico.
Welcome to the New Chemist podcast. Work hard. Be value-driven. You can do it. You can grow and learn it. You can be the difference you and your community needs. Don't give up. We are here, rooting and cheering for you. Don't give up.
Travaillez dur. Soyez axés sur la valeur. Tu peux le faire. Vous pouvez grandir et l'apprendre. Vous pouvez être la différence dont vous et votre communauté avez besoin. N'abandonnez pas. Nous sommes ici pour vous encourager et vous encourager. N'abandonnez pas.
Trabalhar duro. Seja orientado por valores. Você consegue. Você pode crescer e aprender. Você pode ser a diferença que você e sua comunidade precisam. Não desista. Estamos aqui torcendo e torcendo por você. Não desista.
Δούλεψε σκληρά. Να οδηγείτε στην αξία. Μπορείς να το κάνεις. Μπορείτε να μεγαλώσετε και να το μάθετε. Μπορείτε να είστε η διαφορά που χρειάζεστε εσείς και η κοινότητά σας. Μην τα παρατάς. Είμαστε εδώ για να σας ζητοκραυγάσουμε. Μην τα παρατάς.
Trabaja duro. Sea impulsado por el valor. Puedes hacerlo. Puedes crecer y aprenderlo. Usted puede ser la diferencia que usted y su comunidad necesitan. No te rindas, estamos aquí animándote y animándote. No te rindas.
Werk hard. Wees waardegedreven. Je kunt het. Je kunt groeien en leren. U kunt het verschil zijn dat u en uw gemeenschap nodig hebben. Geef niet op. We zijn hier om voor je te roten en te juichen. Geef niet op.
Work hard. Be value-driven. You can do it. You can grow and learn it. You can be the difference you and your community needs. Don't give up. We are here rooting and cheering for you. Don't give up. Thanks for listening. We're glad you were able to tune into this podcast. Once again, this is the New Chemist, where we discuss chemistry, which simply put is the science of change, as well as the other sciences, careers, community, research, and COVID-19. Thanks again for listening. Note, the views on this podcast represent those of my guest and I. You are very important, especially to us here at the New Chemist podcasting group. You listening in is significant.
Vous êtes très important, surtout pour nous ici au New Chemist Podcasting Group. Votre écoute est significative.
Usted es muy importante, especialmente para nosotros aquí en The New Chemist Podcasting Group. Usted escuchando, es significativo.
Você é muito importante. Especialmente para nós do The New Chemist Podcasting Group. Você ouvindo, é significativo.
Είστε πολύ σημαντικοί, ειδικά για εμάς εδώ στο The New Chemist Podcasting Group. Το να ακούς είναι σημαντικό.
Sie sind sehr wichtig, besonders für uns hier bei The New Chemist Podcasting Group. Es ist wichtig, dass du zuhörst.
Je bent erg belangrijk, vooral voor ons hier bij The New Chemist Podcasting Group. Dat je meeluistert, is veelbetekenend.
You are very important, especially to us here at the New Chemist Podcasting Group. You listening in is significant. Okay, this is definitely exciting. Welcome to the New Chemist podcast. We are so glad you are listening. Feel free to download this podcast on Google Podcasts, Apple Podcasts, Spotify, Odyssey, and a variety of other platforms. Here on the New Chemist, we discuss chemistry, which simply put is the science of change, as well as the other sciences, careers, community research, successful student stories, and much more. My co-host for today is Dr. Mike Zott, otherwise known to me as Mike. It's so good to have Mike on the podcast. Thanks for joining.
Yeah, thanks for having me, David.
Yeah, man. Yeah, dude. Good experience. A good opportunity to just chat with you for a bit and let everyone hear your expertise and as I share some of my experiences. So let me just briefly inform the audience about you and then we'll just dive in. So Mike Zott is currently a postdoc at UPenn with Professor Dirk Trauner. Did his PhD at Caltech, the California Institute of Technology, from October 2018 to February 2023. I had the opportunity to attend his PhD defense virtually. Definitely was a treat. He did his PhD in inorganic chemistry with Professor Jonas Peters. He graduated from Georgia Tech, that's where I met him. He did BS in chemistry with a minor in physics and he got a 4.0. He's definitely very accomplished. He has a variety, a myriad of research experiences that aim to provide support for people, chemists, pharmacists, students, enthusiasts interested in the content in educational and intellectually stimulating ways. So refer to the relevant experts if specific advice is needed, whether it be medical or professional. These are just for entertainment and educational purposes only. So yeah, Mike, man, this is good. So how have you been, Mike? Yeah, how you been?
Yeah, I've been very good. Like you said, I defended my PhD several months ago, so it's really nice to wrap that stage of my life up. It was a really fun period of life, but it was also very challenging in ways that you really never expect what the difficulty will be in your PhD. For some people, the difficulty is doing the research. For some people, maybe it's their interaction in a total, or not my PhD, my postdoc, in a totally new area of research, which has been really fulfilling because I went from doing inorganic chemistry, where it's really focused on metals, and in particular metals in the context of sustainable chemistry. And now I've switched over to a field where I'm learning a lot about organic chemistry and the synthesis of complex natural products, as well as continuing in the chemistry, like methodology, that sort of chemistry in the context of sustainable transformations using oxygen as a terminal oxidant and some more interesting iron catalyzed chemistry similar to my PhD work. So there's some similar chemistry I'm doing, and then also some chemistry that's just totally new to me that's been really fascinating to learn about.
Oh wow, this is very interesting. So what caused the switch?
So part of the switch was that I started doing some methodology in my PhD in the realm of organic chemistry. That was a bit different from the, sustainability focused chemistry I was doing for the bulk of my PhD. The chemistry I'm referring to there is converting ammonia into dinitrogen using iron catalysts. And the goal of that research was to study how we fuel in a fuel cell, just like, for example, hydrogen. If you've ever heard of like a hydrogen fuel cell or a hydrogen powered car, something like that. It's, the exact same concept. So that's what I was working on. But then I started doing this project that involved copper catalysts and photochemistry. And there the idea was trying to make ways to make complex molecules in maybe an easier way, but at a very fundamental level. And what I wanted to learn in my postdoc is how I could take these fundamental skills that I was working on in my PhD and apply them to the, challenges that are, maybe larger, where I'm pulling in methodology that many other people across the world and across time have developed in order to make these complex molecules that have really interesting biological properties, as well as just really beautiful, intricate chemical structures.
Okay, so like what? Complex molecules like what?
Like natural products. So I won't say like the molecule I'm working on.
No, you don't have to.
Yeah. But what it looks like is it's kind of steroidal in nature.
Okay.
Aspects that look like the carbon skeleton of a steroid. And then there's some other aspects that are quite different. So,
wonderful, man. Wonderful. So I guess you nod to the Eshin Moses, the Woodwards, the Coreys. You nod to them as you do your work.
Yes, exactly.
You nod
that same class of people. In fact, my building, right when I would get out of the elevator each day, there's a poster of E.J. Corey.
Oh, wow.
So I'd get out and I'd see a picture of him with his Schlenk line back in probably the 70s.
Oh, wow.
Experiments. So that was always an interesting sight as I stepped out of the elevator.
Yeah, I had the opportunity to work with one of his postdoctoral students who was a professor at IU at the time. So he was two of the professors at IU Chem were actually postdocs with E.J. Corey. It's so interesting how the chemistry world, it's big but it's small at the same time. But yeah, dude, so I guess you're kind of curious to know why I made my switch. Are you curious to know as to
Yes,
why?
I'm extremely curious about how you switched from your chemistry background where I met you. I met you at Georgia Tech and you're very excited about chemistry, but you've always been excited about medicine and applying it. And that's kind of similar to how I switched in my postdoc. I went from, fundamental chemistry to trying to do chemistry in an applied way. And I imagine that's kind of similar how you're taking your chemistry background and applying it in pharmacology. So let's hear about that.
Okay, good. See, well, you almost took the words out of my mouth because you're always the same bright person when I met you. But yeah, given that I want to apply it, I want to not just teach it and do research on it. I want to have the opportunity to apply it and help more people. And I see myself being able to do that best through the use of a PharmD. So yes, I have an MS in chemistry, but at the same time, I wanted to apply it not just in the academic and research setting, so in the intellectual arena, but also I want to apply it in a place or in a space where I could see the impact in a shorter time interval. So like with pharmacology knowledge, whether it being understanding how the drug affects the body, so pharmacodynamics, or understanding how the body is impacted by the drug, so pharmacokinetics, so absorption, distribution, metabolism, excretion, those types of things. Understanding those aspects and then applying them well, understanding the drug mechanism of action, understanding the drug class, understanding how it functions in the body, how it's functioning in relation to the endogenous ligand, that type of thing. All of that body of knowledge, especially when applied and when understood well, I think I've seen, I've come to understand and appreciate that it can help people. And so that adds a lot of value, and also it's fulfilling to me, even as I'm learning about it, because it's not, in a way, I wouldn't say it's a homologous transition, like it didn't really come from the same origin, but I would say it's, in a way, it's like orthogonal, but it's very similar, analogous, if you will, because at the same time I'm applying all of the information that I've learned, all of the experiences that I've gained is being applied basically every time I step into the classroom. So I did my MS in chemistry, but I did a concentration in chemical biology and a minor in organic. So some of those things, whether it be first pass metabolism or introduction, having a good understanding of the electron transport chain, porphyrins, like all of the chemistry speak, if you will, is not foreign to me. So it's definitely a good, I came into this program with a good toolkit, and I'm grateful for it. But yeah, Mike, so today me and Mike, we're going to be discussing this article that Mike suggested. So as he's a co-host, so the article is entitled Capturing Primary Ozonides for Syn-dihydroxylation of Olefins. Well, Mike, that's a mouthful. What if you had to summarize that title like in just a few words before we start diving into the content of the paper? What would you say? Of course, this paper was published in Nature Chemistry. How would you simplify it for an regular person or a lay person who is not really familiar with olefins and ozonides? And why should they even care?
Yeah, that's a great question. I would say, at least to start with, the premise of this paper is trying to accomplish a transformation. You know what I mean by transformation? It's just converting the material you put into the reaction into the products. That's the transformation of really common type of chemical called olefins or alkenes that are found in numerous types of molecules. These could be building blocks that maybe a medicinal chemist would use in order to try to make a drug. These are often found in molecules of biological origin. So, for example, many of the molecules in your body, there are olefins in many of them. They're really found in many parts of nature. So this is a general transformation that's applicable to all sorts of molecules that have these olefins in them, or these carbon-carbon double bonds. And then the idea is that you can add 2 oxygen atoms, form of alcohols, onto that double bond and turn it into a diol, and specifically a syn-diol, which means that the 2 oxygens are oriented sort of on the same face. That's how they're added onto this double bond. And the reason this is important is because these syn-diols occur in a number of different
olefins, as Mike spoke about, the double bonds using ozone. Traditional ozonolysis reactions result in the cleavage of the olefin double bond. The article explores a novel approach where ozone is used as a constructive reagent rather than a deconstructive one, aiming to create new chemical reactivity and increase molecular complexity. The authors focus primarily on POZs, so primary ozonides, as preparative synthetic intermediates for green and safe olefin syn-dihydroxylation. So
that's where we have to make, I would say, a really important point, which is the main premise of this paper. So yes, they're doing this transformation where they're going from an olefin to a diol, which is not a new transformation. So the molecules they're making certainly are important. But what's really remarkable about this study in particular is that they're taking a transformation that people have known about for a really long time, ozonolysis. And usually what happens is it breaks the molecule in half. Not necessarily in half, but it cuts it right in the middle of that olefin, that carbon-carbon double bond. But what's really unique and groundbreaking about this particular study is that they're able to stop that process from happening. They're able to interrupt it and retain that carbon-carbon bond, which in this case is kind of valuable, and do a dihydroxylation as opposed to cleaving that double bond all the way into, for example, ketones and aldehydes.
Yeah.
carboxylic acid, some sort of carbonyl compound. So they interrupt this process, and that's really, I think, quite groundbreaking because they're doing it without the presence of any, harmful metals. So, for example, normally the way you would do this transformation, at least one example, is you'd use this compound called osmium tetroxide, which is extremely toxic. It's a metal, but it is also volatile, which means it evaporates easily. So it's very hard to handle in many cases unless you use specially prepared forms of it. And if you're exposed to it, I believe it can even cause issues such as blindness.
Wow. So would you handle something like that in the glove box, or would you not handle it? Glove box.
This is something you would want to use in a fume hood, definitely. People wouldn't typically use it in a glove box, but there are some forms where it's encapsulated in a material that makes it easier to handle. Or there are some like salt precursors where it's not in the form of osmium tetroxide specifically, which is volatile, but it's a salt of it, which makes it, no longer evaporate easily, so you can weigh it out more easily.
Okay, this is good. So some people might have seen some dihydroxylation reactions or some descriptions of dihydroxylation in the oxidation of alkenes with cold potassium permanganate leading to cis-diol, or where you have like hot potassium permanganate leading to two carbonyl compounds, which is what Mike spoke about just a while ago. So ozone. This paper talks about it mentions ozone, which is a powerful oxidant used in various industrial applications, including pharmaceutical synthesis and disinfectants. So typically when we hear about ozone, we hear about the hole in the stratosphere, or the ozone hole. So it's technically not a hole where ozone is present, but it's actually a region of exceptionally depleted ozone in the stratosphere over the Antarctic that happens at the beginning of the southern hemisphere. It's interesting how this involves ozone. Why do you think they chose to use ozone? Is it because of its catalytic nature or reactive nature? Why do you think they chose to use ozone as opposed to using something else to run these reactions? I understand they want to do dihydroxylation, but why did they choose ozone?
I think the reason that they chose ozone in this study is that ozone is a pretty sustainable oxidant because it's generated from oxygen, which is very abundant in the atmosphere. The atmosphere is made up of about 20% oxygen, so it's very readily available. And the only input to generate the ozone is electricity. So the way this usually works in the lab is you have an oxygen tank, which is pretty cheap and non-toxic, at least in dilute concentrations. Of course, it's very flammable, so you have to work carefully with it.
Of course.
But you feed it into an ozone generator, which essentially just looks like, a big rectangle, which you stick a tube in and a tube comes out of it, and you plug it into a wall socket, and it uses electricity to convert the oxygen into ozone. So the ozone comes out the outlet hose, and then you bubble that into your reaction. So it's both easy to generate, and it's also, relatively sustainable as compared to some of the other ways you might carry out this transformation. And in addition to that, it's also very easy to remove. So the ozone, like you mentioned, in the ozone layer, the stratosphere, it's a gas. So it comes out of your reaction pretty easily. So it's easy to get rid of the reagent. So it really has a number of advantages.
Okay, so this is good. So as we progress into some more questions and more discussion, I just thought I would drop this. Why do you think the stratosphere goes to church? Why do you think the stratosphere goes to church? Take a guess.
That is a pretty good question.
Why would the stratosphere go to church?
Let's see. Well, there's the common conception of heaven being in the sky.
Okay, yeah.
So you might consider that, given its proximity being very high up in the sky, it might want to be, I don't know, maybe something like that.
No, dude, it's because it's holy. Oh my goodness. Yeah, dude, it's because it has a hole, so it's holy. But anyway, moving forward, how would you describe your graduate school experiences in relation to this paper? So would you have been able to do this type of work in your lab? Would you have had the time to do something like this? A project that involved working on some type of transformation that's not necessarily novel, but has a degree of expertise? Or would you say you worked on stuff like this in terms of its value and its contribution to the scientific community? How would you...
I would say this is definitely very different from the precise research I carried out, but it is in line with many of my interests in chemistry. So one of my major interests in chemistry, two of them are sustainable chemistry, as well as the generation of methods that are really empowering to researchers in, the synthesis of complex molecules. I'm really interested in both of those areas of chemistry. And I would say that this paper really, if you looked at a Venn diagram of those two interests I just said, it's smack in the middle.
Smack in the middle,
yeah, it's a really powerful method, and it's also, pretty straightforward conditions that many people have access to in, their own laboratories, and it's moving the direction of, pretty interesting sustainable chemistry applications. So while it's totally unrelated to the precise reactions I myself was carrying out, it's certainly aligned with my interests, and I think it's really an amazing paper because it just takes a reaction that you learn in your undergraduate chemistry and kind of flips it on its head in a new way that you maybe wouldn't have thought of. And it's when you get into the details, the chemical details of how they accomplished it, it's a really interesting philosophical approach to the problem, the way they solve this challenge.
So what do you mean by that? It's an interesting philosophical approach. What do you mean by that?
So, for example, I don't want to delve too much into the weeds in terms of the chemistry, but what they do is they perform the reaction at a really low temperature with the olefin, and they do that to stabilize the primary ozonide. So this is the first stage of the reaction where ozone's added to the olefin, and you have a 5-membered intermediate, the 3 atoms of the ozone and the 2 atoms of the olefin. Yep. And then they kick out one of the oxygens of ozone using a strong nucleophile, in this case isopropyl magnesium bromide, a Grignard reagent.
Grignard.
And that allows them to produce the resultant diol product. And it's really, I'd be interested in figuring out how they chose this isopropyl Grignard nucleophile, because it's a really reactive nucleophile. It's sensitive to water, it's sensitive to a lot of conditions, and it was just really an interesting choice of reagent for this transformation that I wouldn't say many people would have just thought of out of the box, like, oh, I'm going to use this reagent to kick out one of the oxygen atoms of a primary ozonide. It's just a really creative solution to the problem.
Yeah, do you think a Gilman reagent or Gannon-Cooper would have worked? What do you think?
That's a good question. I'm not sure.
Okay,
I would guess not.
Okay.
Because I think here they maybe want a harder nucleophile than a Gilman type reagent. Okay. But I'm not really sure. It's just the first report of this chemistry, so I'm sure they're gonna follow up on this and
with more scope.
Yeah, many more mechanistic details and things of that nature.
Wow, this
get a better feeling for how it works. But
this is good. So switching gears as we start to progress in this conversation a little bit more. What worked well for you in graduate school? What would you say? What strategies, because you obviously were successful, you finished. That's definitely a mark of success. What would you say complemented well for you doing well? Complemented well to you while you're in graduate school? Would it be your time management, your scheduling?
Definitely not time management. That's something I keep working on as I get older in my life.
Yeah, same.
Getting better with the calendar, with the scheduling.
Yeah, me too.
Definitely being married helps with that because I have more motivation to spend my time in lab wisely.
Okay, that's fair.
But I would say really the one most important point in my opinion is this echoes a famous article written by, this chemist Carolyn Bertozzi, who won the Nobel Prize relatively recently.
Oh yeah, for orthogonal reactions, right?
Yeah, it's called, the way she calls it is being a closer. And essentially what that means is making sure that you finalize the research projects you're working on. Because it's a lot of fun to try out a bunch of different reactions, start new things. It's a lot more fun in the beginning when you don't have to really dive really deep into all the details. But I'd say the most important thing for myself was being very focused on finishing what I started and making sure I did the experiments to turn my initial hypothesis and initial successful research hit into a completed paper. So doing some of the boring experiments like the characterization data or some of the mechanistic experiments that aren't necessarily fun to do, but they're very important in terms of, making sure your work is academically rigorous, which I would say is one of the most important things as a scientist, being very rigorous with all of the experiments you're doing.
I completely agree. So as we zoom in and zoom out, so mechanistic details, were you doing them computationally, or did you figure them out through the use of NMR and mass spec, or did you use those primarily for your characterization? Just list a few of the tools that you use before we zoom out to a general picture of this.
One of the reasons I wanted to work with my PhD advisor, Jonas Peters, is that I really valued the academic rigor of the work that comes out of his lab. So when we analyze a problem, we use pretty much every tool at our disposal.
Okay.
Which fortunately at Caltech we had a lot of tools at our disposal. So one technique a lot of people did is EPR, electron paramagnetic resonance. I didn't get to do that too much, although I did do it in one of my papers. We had a Moss bar spectrometer in our own group, which I used in a lot of my work. It's a specific type of spectroscopy that works really well for iron containing compounds, which was my specialty. NMR, mass spectrometry, UV vis, electrochemistry, really a lot of different types of techniques.
Okay, that's good, man. That's good. So from a general standpoint, you said so time management is something you're still working on, but your ability to finish what you start. I think that's a very important practice. Being able to complete what you start within reason, and once you understand yourself and know yourself in your context, being able to complete the projects that you start. I think that's very, very important. It's good to experiment, it's good to try new things, but at the same time, discipline and focus, I think, is very, very, very important. So
in your transition to you've made a big transition and you juggle a lot of things. Obviously you're doing a PharmD, you manage this podcast, you're involved with a lot of other really important endeavors. How do you do it?
So how do I do it? Dude, I'll be honest with you. For me, it's accountability. Accountability is a key aspect of this. See, when I vocalize what I'm doing to people, say, I vocalize it to you or to my colleagues, friends, or vocalize it to my family members. When I vocalize it, there's this implicit expectation that you will complete what you started. You won't just drop it and leave it hanging. And also the support system that I have, when I express to them that I'm working on something, they'll come to me and say, so how's it going with that? Or how are you making progress with that? Or how is that fitting into what you have to do? I honestly have people in pharmacy school, which I'm grateful for, and they'll come to me and they'll remember, we expect you to get this grade in this test, this type of thing, or we expect you to be the top, or we expect you to do this, or we expect you to do that. And it's not really focusing so much on people's expectations, but it's having a network of accountability. That is what really helps me to manage all these things, as well as, I do a lot of scheduling. I use Google Calendar and I use a hard copy calendar. And one thing I do, and I'm doing this more in pharmacy school, is I take the text and convert it to an MP3 and listen to it as I'm on the bus or on the train or some walking. So I'm listening to my notes as I'm going along. So I try to use my time wisely and extract the value from it. But yeah, Mike, this is really, really good. This is really, really good. So my question to you is, what advice do you have for future graduate students as we start to wrap up? What advice do you have for future graduate students or people who are currently in graduate school? What advice would you give them as you now serve as your postdoc? So I'm not sure what your future plans are, but you're in a postdoc at UPenn. From our conversations, you seem to be doing fine. What advice would you give to someone who's recently starting who just started the chemistry PhD program?
Yeah, definitely echoes the theme you just talked about, accountability. And I think as a beginning grad student, and I'll say in a research environment, what you want to do is you want to find a really good mentor. I think it's extremely important for a first-year graduate student, at least if it's possible, to work with an older graduate student who's involved with them. And that's not always possible. Sometimes it's difficult to get someone to mentor you, or your advisor maybe wants you to work on a project by yourself. But really, I think it's crucial to find a good older mentor, whether they're in your own research group, or if they're in a different research group, maybe they're in an affinity group, something like that. You just really have to find a good mentor, I would say, in addition to your primary PhD advisor.
Yeah, I completely agree with you. And as we conclude, I completely agree with you in that, mentorship is so important, and you could have different types of mentors. You could have professional mentors, you could have research mentors, you could have people who are mentoring you for where you want to go next. So mentors that are complementing to your network. Like I can listen to my mentors like Stanley Dorn, Dr. Kevin Brown, Dr. Ted Bernansky, Chancellor May, Dr. Bayer, Dr. Langer. Those people have complemented to my development. And, I'm really appreciative for it. So yeah, dude, I completely agree. It's good to find a mentor. And this is the thing you have to remember. The mentor might not come to you. Sometimes you have to go to them or find a time that's convenient for them, or you have to read about their work or reach out to them or send the email. What's the worst that could happen? You send an email inquiring about the work that they're doing, wanting to hear more, or have a conversation, or reach out to people who are interested in, or find out. I've realized that when it comes to academics, or like scientists, it's good when you can read about their work if you have time and find out, so you can ask like salient questions that show that you've done your homework and you are complementing with or you are inquiring with a good bit of background research. So you don't have to like write a thesis on it, but just be aware of the big themes that they have worked on and have discussed. But yeah, Mike, this definitely was a good conversation, good concentrated conversation on this paper, and to speak with you and chat and hear how you're doing. So it was wonderful to have you on as a co-host. You are very important, especially to us here at the New Chemist podcasting group. You listening in is significant.
Vous êtes très important, surtout pour nous ici au New Chemist Podcasting Group. Votre écoute est significative.
Usted es muy importante, especialmente para nosotros aquí en The New Chemist Podcasting Group. Usted escuchando, es significativo.
Você é muito importante. Especialmente para nós do The New Chemist Podcasting Group. Você ouvindo, é significativo.
Είστε πολύ σημαντικοί, ειδικά για εμάς εδώ στο The New Chemist Podcasting Group. Το να ακούς είναι σημαντικό.
Sie sind sehr wichtig, besonders für uns hier bei The New Chemist Podcasting Group. Es ist wichtig, dass du zuhörst.
Je bent erg belangrijk, vooral voor ons hier bij The New Chemist Podcasting Group. Dat je meeluistert, is veelbetekenend.
You are very important, especially to us here at the New Chemist Podcasting Group. You listening in is significant. Welcome to the New Chemist podcast.
Bienvenidos al podcast del nuevo químico.
Καλώς ήρθατε στο podcast του New Chemist.
Welkom bij de podcast van The New Chemist.
Bienvenue sur le podcast du nouveau chimiste.
Bem-vindo ao podcast do novo químico.
Welcome to the New Chemist podcast. Work hard. Be value-driven. You can do it. You can grow and learn it. You can be the difference you and your community needs. Don't give up. We are here, rooting and cheering for you. Don't give up.
Travaillez dur. Soyez axé sur la valeur. Tu peux le faire. Vous pouvez grandir et l'apprendre. Vous pouvez être la différence dont vous et votre communauté avez besoin. N'abandonnez pas. Nous sommes ici pour vous encourager et vous encourager. N'abandonnez pas.
Trabalhar duro. Seja orientado por valores. Você consegue. Você pode crescer e aprender. Você pode ser a diferença que você e sua comunidade precisam. Não desista. Estamos aqui torcendo e torcendo por você. Não desista.
Δούλεψε σκληρά. Να οδηγείτε στην αξία. Μπορείς να το κάνεις. Μπορείτε να μεγαλώσετε και να το μάθετε. Μπορείτε να είστε η διαφορά που χρειάζεστε εσείς και η κοινότητά σας. Μην τα παρατάς. Είμαστε εδώ για να σας ζητοκραυγάσουμε. Μην τα παρατάς.
Trabaja duro. Sea impulsado por el valor. Puedes hacerlo. Puedes crecer y aprenderlo. Usted puede ser la diferencia que usted y su comunidad necesitan. No te rindas, estamos aquí animándote y animándote. No te rindas.
Werk hard. Wees waardegedreven. Je kunt het. Je kunt groeien en leren. U kunt het verschil zijn dat u en uw gemeenschap nodig hebben. Geef niet op. We zijn hier om voor je te roten en te juichen. Geef niet op.
Work hard. Be value-driven. You can do it. You can grow and learn it. You can be the difference you and your community needs. Don't give up. We are here rooting and cheering for you. Don't give up. Thanks for listening. We're glad you were able to tune into this podcast. Once again, this is the New Chemist, where we discuss chemistry, which simply put is the science of change, as well as the other sciences, careers, community, research, and COVID-19. Thanks again for listening. Note, the views on this podcast represent those of my guests and I.